Hey, AP Statistics. So today we're going to kind of wrap up experimental design. We're going to get into a couple of other details of it. So the first thing is block design. This is another kind of a more advanced experimental design. We had our completely randomized design in the last one where you just take your subjects, you split them up, and you compare, you split them into the treatments, compare at the end. So block design is very similar to stratified random sampling in a way. And so people get them confused, but I mean, basically, the kind of some of the ideas are the same for why we do them and how we do them. But realize that block design is an experimental design, and so you just got to kind of memorize these terms and these differences. Block design is an experimental design, and then stratified is a random sampling is a type of sampling. So don't get those confused, and let me show you kind of where they're the same. So what we used to call strata in there. So blocks are a group of experimental units that are known before an experiment to be similar in some way and in a way that is expected to affect the response to the treatments. And so in a randomized block design, the random assignment of experimental units to treatments is carried out separately within each block. So let's say, again, that we have like gender or something we think is going to be related to a response variable. Well, if I just did pure random assignment, I might just by chance end up with more boys in one group or more girls in another group. And so then similar to like with our sampling methods where that kind of skews the results, that can kind of skew the results. It's not biased to not do so, but just it leaves more up to chance. So in a block design, we're not going to leave that up to chance. What we do is we basically take each group, in this case, instead of calling them strata, we call them blocks. We take each block and then we randomize within a block. So I take all my boys and I randomize within my boys and I get half the boys into treatment A and half the boys into treatment B. And then do the same for the girls, half into treatment A and half into treatment B. And so that allows us to account for the variation in the response that is due to the blocking variable. Overall, it should make our results, more precise, and we can even do a few other different things with this. This makes it easier to determine if one treatment is really more effective than the other. We're leaving less up to chance and not saying that because we happen to get more boys or girls in one group or the other, that then the responses are different because of that. And again, that's not biased. It's not poor design. It's just we could be better by controlling for that variable we think might affect it. Randomness should get about the same number in each, and if you get a big enough, you do enough replication, it should be fine. And when blocks are formed wisely, it is easier to find convincing evidence that one treatment is more effective than another. So here is an example where we had some individuals, we had 10 volunteers, and we were trying to study like the effect of different keyboards on how fast they can type. And so we started with 10 volunteers. And then what we did is we realized that individuals that, depending on whether they were using a smartphone already or not, that we thought that would affect their speeds with this. So we actually did 2 blocks. And you notice these blocks don't have to be the same size. We have 4 that were and 6 that weren't. This split here is not random. This is some pre-existing feature of our individual. This step is not random. Then once we split them into their groups, and like this could be genders, right? This could be boys and girls, and we don't randomly assign people a gender. We split them up there, and then we go through the process of random assignment. Now, once we have them in their blocks, we split the blocks up, and we could have more than 2 treatments, but here we have 2 treatments. And so of the 4, 2 got keyboard A, 2 got keyboard B, and then we would compare within those. And then of the 6 we had 3 got keyboard A, 3 got keyboard B. And so then here we're comparing smartphone users and comparing treatment A and treatment B. And then down here, we're comparing non-smartphone user and comparing A and B. And so we may see different results. We may see for the smartphone user, keyboard A performed way better than keyboard B. And for the non-smartphone users, it might be keyboard B was better than A. Or maybe there was no difference. Or A was better, but not a big a difference. So then you can ultimately compare those. A was better for these group, and B was better for this group, or and so on. So a lot of different comparison can be done with that. And you could have more than 2 blocks and more than 2 treatments, and so on. But that is the block design. If you want to take block design kind of even further, we can go all the way to matched pairs design, or even sometimes like it can be actually matched like 3s and 4s or whatever. So if you get so kind of tiny in your blocks that they become like pairs of individuals, right? So blocks were group people by their similarities, right? So these individuals are similar. So matched pairs design is an experimental design for comparing two treatments that uses blocks of size 2. In matched pair design, two very similar experimental units are paired, and the two treatments are randomly assigned within each pair. In others, each experimental unit receives both treatments in random order. So you can pair either with somebody who's very similar to you or two individuals that are very similar to each other. We also will sometimes compare someone to themselves. They'll actually do a matched pairs design where like each individual will do both treatments, and you randomize the order that you do the treatments in. So the idea to create blocks by matching, the idea is to create blocks by matching pairs of similar experimental units, just as with other forms of blocking. Matching helps account for the variation due to the variables used to form the pairs. So real quick example, maybe we're trying to study some sort of weight loss treatment. Well, we could just say we're going to try treatment A for half our group and treatment B for half our group. Well, maybe the amount of weight loss you experience is related to what your starting weight is, or some other variable related, similar to that. So instead of just kind of totally randomly assigning, we might group into groups. So you might group into blocks where it's like, okay, here is our obese or our overweight versus, different groups, and you might do something like that, and you go into blocks. Well, you could get down to the very fine detail of, all right, I'm going to take my two heaviest people, and they're going to be compared together. Right, and one's going to get treatment A, one's going to get treatment B, and we'll kind of compare their results. And then we'll do the same with the next two, and the next two, and the next two, and so on. So you might do some sort of comparison like that, and then you can see kind of a real fine difference, related, how it relates to that variable that we do that, and that should make our results more precise again. Or you might have an individual compare to themselves. You can do it in some cases, you can't in others. Like weight loss, it's kind of hard. You can't compare yourself. I can't do like one late weight loss plan and then like, I don't know, am I supposed to gain the weight back and then try the other one? Like it doesn't work real well. But in other situations, it might work well where you want to try one treatment. Like again, if individuals are wildly different, like if you're trying out different types of like sports equipment, you want to see if a particular type of like baseball bat is better than another, right? You don't want to like assign half people to one or another. You probably have each person try it both ways, right? And so in that case, it should be fine, right? You have each person. You might have one person who steps up and tries it kind of one way, and then the other way, and then the next person tries it, and you can kind of compare the results for each individual, because how far they can hit the ball with a baseball bat varies quite a bit from individual to individual. So it'd be better to do those comparisons than like a completely randomized design. So by the end of this, you should have learned a whole bunch of vocabulary. Your head might be swimming, so pause, take your time, maybe do some flashcards or something like that. A whole bunch of more vocabulary to know regarding experimental design.